Welcome to our YouTube channel. In this video, we are going to calculate wind load based upon Indian standard. In the right hand side, you can see IS 875 Part 3 2015, which is the code required to calculate wind load based upon Indian standard. In the left hand side, you can see an Excel sheet which is developed to demonstrate for wind load calculation as per Indian standard. The first input required is basic wind speed. This generally we can able to get from technical specification, or if it is not given, we can also refer to IS 875 part 3 figure 1. For that we need to go to page number 3. So this map, based upon the location of the project, we can able to pick the basic wind speed VB from this map. Suppose if my project is located in Chennai, so you can see that red color. So in the legend you can see that wind speed for the color scheme is 50 meter per second. So we can consider the same as per that. Alternatively, if the project location is in the site which are listed in Annexure A, that means page number 54 to be referred. So here there are some important cities and towns are listed here in this Annexure A. Based upon that, basic wind speed also provided according to this. So we can also pick from here if the project location is within these listed cities, or else the best option is in page number 3. We need to refer the map. So this will provide you all the major cities and even some towns. So based upon the map, you can able to pick the exact basic wind speed. So next information we need is a probability factor or a risk coefficient K1. So this we need to refer table 1. For that, page number 10 we have to go. So here in this right hand side you can see the table 1, which is for a risk coefficient. So this can be categorized as 4 numbers. Mean probability design life of structure in years 50, 5, 25 and 100 years. So we need to select from this. If it is 25 years, means 0.7 for basic wind speed 50 meter per second. So for 25 years it is 0.9. So you can see in the right hand side, for 50 meter per second of basic wind speed for 25 years it is 0.9. So for 50 years it is 1 for 50 meter per second. So we can consider as 100 years of design life, so that K1 factor is 1.08 for 50 meter per second. So here in this right hand side of Excel sheet table, you can see that the extract of IS 875 part 3. So this table in the right hand side of IS 875 part 3 is extracted to here, so that it can be easily picked from the value when we are selecting this drop down list. So we got find out the risk coefficient factor also for 100 years. It is 1.08. Next information we required is the terrain roughness and height factor K2. For that we need to select the category. For category definitions, we need to refer class 6.3.1 of IS 875 part 3. This is available in page number 8. So it start from here, category 1, exposed open terrain with few or an obstruction. So in the left hand side Excel sheet, the same is extracted here. So for category 1, it is exposed to open terrain with few or no obstructions and in which the average heights are less than 1.5 meter. In the category 2, the obstructions are having the height range of 1.5 to 10 meter. And in category 3, it is obstruction structures are having height more than 10 meter. And the category 4 means it is a terrain with numerous large, high, closely spaced obstructions. So likewise, we have to define the category here in this list. So we can consider category 2, that is open terrain with well scattered obstructions having heights generally between 1.5 to 10 meter. Next one is height, exposed height. We record this information. We can assume our structure height is our structure height along with this apparatus as a 30 meter, so that the terrain roughness and height factor can be get from table 2 of IS 875 part 3. So we need to go for page number 11. So here in the right hand side PDF you can see the table 2, factors to obtain a design wind speed variations with the height in different terrains. So this table also again extracted in that Excel sheet in the right side tab, tables of code reference. So based upon the height wise it is entered here. So while we are selecting this category and entering the height, this K2 is directly picked up from this right hand side tabs, which are calculated are with using interpolation method. So then K2 factor is 1.12. Next one is a topography factor K3 we need to find out. For that we need to refer class 6.3.3.1 of IS 875 part 3, that is in page number 8. So here you can see the topography factors. So here the topography factor is, so here it is mentioned that the value of K3 is confirmed in the range of 1 to 1.36 for slopes more than 3 degree. So for if the slope is below and below that 3 degree, the value of K3 may be taken as equal to 1. So if our site, the destination of the structure, if it is having less than 3 degree of a slope, then we can directly consider K3 as 1. But in case of where there is a slope topography which we are having in our project, means we need to consider this K3 factor as per annexure C of IS 875 part 3. So for that we need to go page number 57. So here you can see the annexure C in the right hand side PDF file. So here there are definitions are given here. L equal to actual length of the upward slope in the wind direction. You can see in the picture here, whereas L is the starting point of the slope and the mid, that is apex or crest of the slope. We are considering for our design purpose as per this picture. It is given in the technical specification that the slope of the hill is 1:3 and height of the hill from the average ground level also given as 150 meter, that is a Z value. So in the right hand side also the definition is given, Z is equal to effective height of the topography feature, location of a structure base from average ground we are considering as 100 meter. In the picture you can see that from the average ground to base of the structure is 100 meter, that is h is equal to 100 meter. And we can also calculate the actual length of the wind up upwind slope in the wind direction L, that is distance from the start of the slope to the peak of the slope L equal to Z into 3, that is a 3 is a slope value of horizontal component. 1 is to 3 here defined is 1 vertical and 3 horizontal. So we are multiplying this value 3 into Z and we are getting L value as 450 meter. Angle of inclination is a tan inverse of Z by L. So that we are getting 18.42 degree. So which is greater than 17 degree. Why we are referring this 18.42 degree to 17 degree is this is as mentioned in Annexure C. In Annexure C, there are two categories to find the K3 factor. One is the slope, which is in between 3 degree and 17 degree. We have to use these formulas to find the K3 value. And if the slope is greater than 17 degree, we need to go another two set of formulas. So for that, we need to calculate whether the slope is more than 17 degree or within 3 and 17 degree. So that we had checked here and find that it is more than 17 degree. So we need to find out other parameters such as value of C and value of SO to find out factor K3. Here in the right hand side you can see the formula to find out the K3 value is K3 equal to 1 plus C into SO. So for finding C, you can find out just below that table format like slope. If it is 3 degree to 17 degree, we need to find out 1.2 into Z divided by L as C value. And if the slope is more than 17 degree, then we can directly consider 0.36 as a value for C. So for us, the slope is more than 17 degree. So we can consider 0.36 here. Or else if it is 16 degree means, so we have to multiply this 1.2 with Z divided by L to get C value. Similar like we need to find out other value called S0, S0. So for that the definition is given here. The factors S0 should be determined from figure 4 and figure 14 for cliffs and escarpments and for ridges and hills respectively. So now for that we need to calculate LE, that is effective horizontal length of the hill depending on slope as indicated in figure 13. So here in the figure 13 you can see here. So LE we need to find out and we already having HL and we need to find out X. X distance is nothing but the distance from the apex, that is crest, to the location of the structure base. So here in the left hand side picture you can see X is equal to 150. How we have arrived this is using this formula L minus H divided by tan phi s. So tan phi s is nothing but the distance from here to this structure base, that is the start of the slope to the structure base. We can directly apply the H divided by tan phi. There is a trigonometry formula we used to say that opposite by adjacent equal to tan theta. So by applying this formula, we can find this value. Then this value to be deducted from the L value, that is the length between the start of the slope to the apex, 450. So likewise, this formula is applied and we had find out the distance of a structure base from crust is x is equal to 150 mm. Similar like we need to find out effective horizontal length of the hill. So this is also defined in class C2. So for that we need to refer this value. So for slope 3 to 17 degree, we can consider the value of L directly for LE. If the slope is greater than 17 degree, then the formula we need to apply to find out LE is Z divided by 3. So we are having Z as 150 and divided by 0.3, we are getting 500 meter. So after finding this X value, LE value, then we need to find out the value of S naught using the figure 15. So in the right hand side you can see the figure 15. So here it is showing a graphical representations to find SO. So you can see that um, the parabolic curve which is showing S naught start from 0.05 to S naught equal to 1, which is inside. So we already having the value of x by LE. So x by LE we are applying here as and we are getting 0.3. H by LE is 0.2. So in order to find S naught value, we required H by LE value and X by LE value. So we had find out the same thing. And from this graph, if you see XLE is located, it is a positive value and it is located here in between 0.6 and 0.4. That is 0.3 is located in between 0.4 and 0.6. And similar like H by LE is 0.2 for our calculation, and this is laid also in between 0.6 and 0.4. So we can consider SO as 0.5. So we are entering here as 0.5. So finally then we can able to calculate the K3 factor, that is topography factor, by applying the formula given in the class C2. Here in the right hand side you can see that is K3 equal to 1 plus C into S naught. So I am applying here 1 plus C value is 0.36 and S naught is 0.5. Multiplying these two and adding 1, I am getting 1.18. So thus we need to find out this K3 factor. Next one is important factor for cyclonic region. So for that we need to refer page number 11. So in page number 11 and 12, you can see that important factor for cyclonic region, the east coast of India is relatively more vulnerable for occurrence of severe cyclones and the west coastal Gujarat in vulnerable of severe cyclone studies. So we need to consider this cyclones studies also. So in this simple form of selecting the K4 factors are given. The first category is structures of post-cyclonic importance for emergency services such as cyclonic shelters, hospitals, schools, communication towers. We need to consider the factor of K4 as 1.3. For industrial structures, it is 1.15. All other structures, it is 1. So we can consider here as industrial structures, and the factor for K4 is 1.15 here. So next we need to calculate the design wind speed Vz. This is as per class 6.3 of IS 875 part 3. For that page number 8 to be referred. So here you can see the formula to find out Vz, that is design wind speed, which is equal to Vb into K1 into K2 into K3 into K4. We already having these values Kb, V1, sorry K1, K2, K3, K4. So simply multiplying all the factors and values, that is Vb into K1 into K2 into K3 into K4, we are getting 82.08 meter per second as a design wind speed Vz. Next one is we need to find out the design wind pressure Pz, which is equal to 0.6 Vz square divided by 1000. So this we need to refer class 7.2 of IS 875 2015. So for that page number 12 to be referred. So here you can see 7.2 class. So it is mentioned Pz is equal to 0.6 Vz square. So here the wind pressure at height Z in Newton per meter square. So we are dividing this value divided by 1000 to get kilonewton per square meter. So just simply applying this Vz value in this formula, we are getting 4.04 kilonewton per square meter. Now next we need to apply this uh, wind design wind pressure into a structure. So how we are going to apply, let's we see that. So for that, in the right hand side of Excel sheet you can see that some picture which is having, which is to be considered as a tower having a three segments. The first segments is mentioned in red color, the second is red color, the second segment is mentioned in blue color, and the fourth one is mentioned in pink color. So the total height of the tower is considered as 30 meter. Each segment is having a 10 meter, and the forces, wind forces, are indicated as F1, F2, F3 respectively to the each segment, and the height of load, that is center of load point, is defined as a centroid of each segment from the base, that is 5 meter, 10 divided by 5 meter, and 10 plus 10 half of the height of the second segment equal to 15 meter, where the F2 is applied. And similar like for third segment, it is summation of two segment height, that is 10 plus 10 equal to 20, and half of the second third segment, that is 10 divided by 5, which is equal to 25 meter. So likewise the center of load acting also calculated in this sketch. Also the base of the tower is considered as 3 meter. So this is a tentative structure parameters which we had considered. Also this structure is having a bracing, 3 number of bracing per segment. You can see it is a cross bracing. So we are going to calculate now the solidity ratio. The solidity ratio is nothing but the ratio between the net area exposed to wind AN to the cross area. That is, for example, I am giving here to how to calculate the gross area. Gross area is nothing but width of the segment, that is 3 meter here, into height of the segment, that is 10 meter. So 3 divided by 10 is 30 meter. So next one is net area. Net exposed area is nothing but what are the exposed member which are exposed to wind, we need to calculate. So here in this segment, first segment we can consider By ignoring that horizontal member, we are going to consider only the main leg and the cross bracing. So there are two main leg which are going to exposed. So considering the main leg sizes angle section of 200 by 16, so that it will be 2 into height is 10 meter, as it is the section size is 200, it is 0.2 meter. So 2 into 10 into 0.2. 200 is a 200 mm is a size of the angle. Similar like the cross bracing, we are considering as angle size of 80 by 8 mm, so that there are three number of angles. So it is 3 into, considering the approximate length of each cross bracing is 4 meter. So it is 4 meter and the size is 80 mm or 0.08 meter. So applying this, we are getting 0.96 square meter for all the three bracing. So summation of this main leg and cross bracing, we are getting 4.96 square meter. So then the solidity ratio is AN1 divided by AG1, that is net area divided by gross area of first segment. So that is 0.17 is a solid ratio. Similarly, for all the two other segment also, same kind of methods we need to adopt, as all the other two segment are similar like the first segment. We can consider the same solidity ratio. By using this solidity ratio, we need to find out the force coefficient. This is as per table 33 of IS 875 part 3. For that, we need to go page number 46 in the right hand side PDF. So you can see in the right hand side standard code IS 875 part 3 table 3. This is overall force coefficient for towers composed of flat sided members. So this is the table. This table also extracted here in the Excel sheet, right side tab, tables of code reference. So here you can see that based upon the solid ratio 0.1, 0.2, 0.3, 0.4, 0.5 respectively, for square tower and equilateral triangle towers, the values are entered here. We are considering our tower as a square tower. Square tower is nothing but if you are having four numbers of leg member, then that can be called as a square tower. The equilateral triangle tower is a tripod type of towers. For that, the coefficient factors are provided here. So we are considering the square type of tower, that is four-legged tower. So then from the table 33 for solidity ratio 0.17, we are getting force coefficient factor CFS 3.45, which is interpolated here in the right side Excel tab. So next one is we need to calculate the wind force on each panel. For that formula is F is equal to phi, that is solid ratio, into gross area into PZ. PZ is a design wind pressure. For panel 1, F1 equal to phi. Phi is common for all the three panels. Panel or segment, we can call it as phi into AG1 into PZ. AG1 is a gross area of panel 1. PZ is a design wind pressure. So for panel 1, AG is 30 square meter and PZ is 4.04 kilonewton per square meter. Phi value is solid ratio is 0.17. By multiplying this, I am getting 20.6 kilonewton. as a force. So this 20.6 kilonewton value seems to be wrong because we are our K2 factor is wrong, which we had entered, because this K2 factor is depends upon the height of the structure. So here we had entered H as a 30 meter, but that is wrong totally, because we need to find out each individual segment, means we need to enter the segment height, that is panel height. So panel height is 10 meter. So for 10 meter panel height, we are getting 16.42 kilonewton. So if we want to find out for total height, that is total height of the tower, we can enter here as a 30 meter. So we are getting 20.6 kilonewton for the total height. So we can enter here for individual segment. So it is 10.62 kilonewton. How to find the bending moment or moment at the base of this first segment is M1 into, sorry, M1 equal to, M1 is a bending moment, equal to F1 into Y1. So this F1 to be multiplied with 5 meter. We had arrived here that Y1 as 5 meter. So likewise we need to calculate the moment at the base of every segment. So here is a summary of the total height of the tower with various segment. So for first segment we are having the height up to 10 meter. Second segment the height up to 20 meter, that is 10 plus 10. For the third segment the height is up to 30 meter, that is total height of the tower is 30 meter. Adding the three segment 10 plus 10 plus 10, we are getting 30 meter. So likewise we need to enter here the height of the each segment which are exposed to wind. Accordingly the K2 factor is extracted from the adjacent table and calculated using interpolation method. So for 10 meter it is 1, for 20 meter it is 1.07, for 30 meters it is 1.12. So these values are extracted from the table and added here. Then Vz is according to the formula, it is calculated Vb into K1 into K2 into K3 K4. Here the value K2 is going to change according to the height, so that this K2 alone is taken from this above cells. So likewise I am having the Vz value similar like Pz is nothing but it is 0.6 into Vz square divided by 1000. So the same formula is applied here and I am getting Pz for each individual segment. And F is the force which is we calculated here. F is equal to 5 into Ag into Pz. So that Ag value is common for all the three segments, 30 square meter, and 5 value also common for all the segment or all the panel, 0.17. So multiplying those value into this Pz, I am getting this as a force 16, 18 and 20 kilonewton approximately for each segment. And similarly we know that Y value is 5 meter. In the sketch you can see 5 meter for first segment, 15 meter for second segment and 25 meter for the third segment. So I am entering here 5, 15. So finally the moment at the base of every segment I am calculating here as 82, 282 and 515 kilonewton meter for every segment, and I am summing, I am adding all the forces of every segment to get the total value at the base is 55.84 kilonewton. Similarly for movement it is 879.40 kilonewton meter. So this is how we need to calculate wind load based upon Indian standard IS 875 Part 3 2015. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.